Hi, this is Dick Gross back again with Fat Chance. Well, we've reached the final unit of this course, and in this unit, we're going to consider the calculation of probabilities in situations where we can really only estimate the answer, as the full calculation is just too time-consuming. So to illustrate this, suppose we ask for the probability of getting at least 6 heads in 10 flips of a fair coin. Well, we know how to calculate the answer. First, you calculate the probability of getting exactly 6 heads, which is 10 choose 6 divided by 2 to the 10th. Then you add the probability of getting exactly 7 heads, which is 10 choose 7 divided by 2 to the 10th. Then 8 heads, and 9 heads, and 10 heads. You add those 5 terms up. That's the probability of getting at least 6 heads in 10 flips. That's not too bad. But suppose we wanted to calculate the probability of getting at least 60 heads in 100 flips of the coin. Well, for each number between 60 and 100, we can calculate the exact probability of getting m heads. That's 100 choose m divided by 2 to the 100th power. That might be an interesting thing to calculate, but even if we did that, we'd have to add up the 41 terms where m is 60, 61, 62, up to 99 and 100. And if we wanted the probability of getting at least 600 heads in 1,000 flips of a coin, we'd have to add up 401 terms, each of the form 1,000 choose m over 2 to the 1,000th power, from m running from 600 to 1,000. And if we ask for the probability of getting at least 600,000 heads in 1,000,000 coin flips, it only gets worse. Well, the miracle is that we can estimate these probabilities closely, as well as the probabilities resulting from any large number of Bernoulli trials, using a wonderful mathematical object called the normal distribution. And in this process of estimation, the subject of probability is transformed into the subject we call statistics. Well, before we get to the normal distribution, which is sometimes called the Gaussian, after the mathematician Carl Friedrich Gauss who worked on it, we will want to introduce the notion of a game. And for us, a game will consist of a single event with a finite number of outcomes. And say the outcomes are P1, P2, up to Pn. And each outcome should occur with some probability and should have some fixed payoff. We'll say the probability of outcome Pi is little pi, and the payoff is AI units. And the probabilities have to satisfy the identity that P1 plus P2 plus P3 up to Pn is equal to 1, as some outcome must occur. The payoffs can be arbitrary. They can be positive numbers of units or negative numbers of units. Well, we've already defined the expected value of a game, which we denote by EV of g, by the formula. EV of g is P1 times A1 plus P2 times A2 all the way up to Pn times An. Namely, it's the sum of the probabilities times the payoffs of the different events. It can be positive, it can be negative. For example, we've studied one form of the game, Chuck-a-Luck, where you roll 3 dice. If no 6 appears, the payoff is 0. If you get either 1 or 2 6s, the payoff is 2. And if all the die come up 6, you get a payoff of 27. That's the payoff of 2 plus an extra bonus of 25 units. So in this game of Chuck-a-Luck, there are 4 possible outcomes. P1, no 6 occurs. P2, 1 6. P3, 2 6s occur. And P4, all the die come up 6. And we know how to calculate their probabilities. From the unit on Bernoulli trials, the probability of no 6 occurring is 5 6 cubed, which is about 0.589. The probability of 1 6 occurring, well, you have to say in which place it occurs. There are 3 choices. And the probability of it coming up a 6 in that place is 1/6. The probability of coming up no 6s in the other 2 places is 5 6. So you get 3 times 1 6 times 5 6 squared, which is about 0.347. And similarly, the probability of getting 2 6s is 3 times 1 6 squared times 5 6, which is about 0.069. And the probability of getting all 6s is 1 6 cubed, which is about 0.0046. And those probabilities all sum up to 1. The respective payoffs in this game, well, if no 6 appears, the payoff is 0. If either 1 6 or 2 6 appears, the payoff is 2. And if all 3 dice come up 6, the payoff, we said, was 27. OK? So we can now do the expected value of the game. You take the sum of the probabilities times the payoffs. The probability of no sixes was 0.589. You multiply that by 0. You add the probability of 1/6, which is 0.347, times the payoff, which is 2. You add the probability of 2 sixes, 0.069, times the payoff, which is 2. And finally, the probability of all 3 sixes, 0.0046, times the payoff, which is 27. And that adds up to an expected value of 0.958. There's another important number associated to any game, which is called the variance of the game. And the variance measures how much the individual payoffs in a game differ from its expected value. It's defined by the formula where you sum up the probabilities times the square of the difference between the payoff and the expected value. So it's P1 times A1 minus the expected value squared, plus P2 times the payoff A2 minus the expected value squared, all the way up to Pn times An minus the expected value of G squared. So to calculate the variance, first you have to know the expected value. Now, notice that all the terms in the definition of this variance, which is always denoted sigma squared of G, have the form Pi times Ai minus the expected value squared. The Pi is a number between 0 and 1. The Ai minus the expected value is a square, so it's non-negative. So all the terms are non-negative. You add them up. The variance is always non-negative. And since it's non-negative, it has a positive square root. And the square root of the variance, which we denote just sigma of G, is called the standard deviation of the game. Given the standard deviation, you can get the variance by squaring it. Given the variance, you get the standard deviation by taking its positive square root. For the game of Chuck-a-Luck, the variance can be calculated because we know the expected value. It's the probability of no sixes, 0.589, times the payoff minus the variance, 0 minus 0.958 squared, plus the probability of 1/6, which we saw was 0.347, times the payoff minus the expected value, 2 minus 0.958 squared, etc. You add those all up, you get about 4.11. And then if you wanted to know the standard deviation, you take the square root of that, which is about 2.03. Well, let's calculate the expected value and variance for another game, the unfair coin toss, where heads occurs with probability P and tails occurs with probability 1 minus P. And we'll assume the payoff for heads is 1 and the payoff for tails is 0. Well, the expected value is the probability of heads times the payoff, which is 1, plus the probability of tails, 1 minus P, times the payoff, 0, and that adds up to P. And the variance, now that we have the expected value, is the probability of heads, which is P, times the payoff minus the expected value squared, which is 1 minus P squared, plus the probability of tails, which is 1 minus P, times the payoff minus the expected value, which is 0 minus P squared, and that works out to P times 1 minus P. When the coin is fair, so the probability of heads and the probability of tails are both equal to 1/2. The expected value is 1/2. The variance is 1/4. And so the standard deviation is again 1/2. Now, for the rest of this talk, we're going to see what happens to the expected value and the variance of a game when we make some very simple modifications to the payoffs in the game without changing any of the probabilities. For example, suppose we decide to increase each payoff of the game by the same amount C. So if the old payoff for the event Pi was AI, it is now AI plus C, the same amount. And we'll call this new game G plus C. What's its expected value? Well, the expected value is the sum of the probabilities times the payoffs. Every payoff has been increased by C. So we get the sum of the probabilities times the original payoffs, plus C times the sum of the probabilities. And the sum of probabilities is 1. That last number is just C. So the expected value of the game G plus C is the expected value of the game G plus the constant C. Okay. Now, since we're just adding C to the expected value, we can choose C, so the expected value of the new game is 0. Namely, just choose C to be minus the expected value of the original game. And now we have a new game, G plus C, where the expected value is 0. What is the variance of the new game G plus C? Well, sigma squared of G plus C is the sum of the probabilities times the payoffs minus the expected value. The new payoffs are AI plus C. We have to subtract the expected value of G plus C. But the expected value of G plus C was the same as the expected value of G plus the constant C. And therefore, if we subtract that off, the C's cancel, and we get the variance of the original game. And the reason that the variance of the game remains the same when we add a constant to all the payoffs is that we're adding the same constant to the expected value, and so the differences of the expected value and the individual payoffs are unchanged. Well, another simple way to change a game is to multiply the payoffs by the same amount, say D. We'll call this game D times G. The individual payoffs are now D times AI, and the probabilities remain exactly the same. The expected value of the game D times G is just the expected value of the original game times D, because when you sum up the sum of PI times DAI, that's D times the sum of PI AI. So you just multiply the expected value by D. What happens to the variance? Well, sigma squared of D times G is the original probabilities PI times the payoffs, which are now DAI, minus the expected value of DG squared. But the expected value of DG is D times the expected value of G. And so inside of this thing we're squaring, we've multiplied everything by D. And so we multiply its square by D squared. And so the variance of the new game is just D squared times the variance of the original game. Notice that if the original game has the expected value 0, then the multiplied game DG also has expected value 0. And if the variance is non-zero, we can choose this constant of multiplication so that the variance and standard deviation of this multiplied game DG are both equal to 1. And such a game, where we set up the expected value to be 0 and the standard deviation to be 1, is called a normalized game. And we've just seen how with no change in the probabilities at all, but making some very simple changes to the payoffs, we can turn any game into a normalized one. In fact, the modified game G0, where you take G, you subtract its expected value, and then you divide by its standard deviation, is normalized. Its expected value is 0, and its variance is 1. And when we have a normalized game, you have very simple formulas for the expected value and variance. The sum of the PI-AI, which is the expected value, is 0. And since the expected value is 0, the formula for the variance is simpler. The sigma squared is just the sum of PI times the AI squared, and that's equal to 1.